Hi, my name is Aditya Ray, and this is my master's thesis video. Look at a murmuration of starlings. There are hundreds of thousands of birds moving as one fluid organism with no conductor. Or let's look at the Shibuya crossing in Tokyo, where there are thousands of pedestrians navigating each other in perfect fluid chaos, with no traffic controller deciding who goes where. Or in financial markets, where the collective behavior of millions of individual trades produces crashes, bubbles, and discoveries that no single trader planned. The same principle underlies all three behaviors, which is order, that's arising from purely local decentralized interactions. And this is known as emergence. And it's the defining puzzle of complex system science. In all these cases, we can observe the collective result, but what we can't see directly is the hidden logic, the purpose or the objective that's driving each individual. This thesis asks the inverse question. Given only the emergent behavior, can we mathematically reconstruct the rules of the game that produced it? Can we essentially reverse engineer collective intelligence? And our goal in this overall thesis is to uncover this game and this purpose that drives our agent behavior. And we've done this in two phases. So first, we've validated that the inversion is actually possible on systems where the rules are actually known, and then we apply it to systems where the rules were never designed as a game at all. In the first phase, we tested our pipeline on Schelling's segregation model. We encoded the governing utility function and asked if our algorithm could rediscover it from agent behavior data alone. The short answer is yes. We discovered a utility function that reproduces hallmark phases of Schelling dynamics, but we couldn't recover the exact utility function itself, which was a fundamental identifiability problem. We then looked at the Reynolds flocking model. Here, our result was very apparent. Our discovery method achieved perfect recovery of the underlying force and torque dynamics, but only after we identified and removed a subtle data corruption. Once filtered out, the true game emerged exactly. Our most exciting result actually came in phase 2 of this project. We took the classic Reynolds-Boyds model, 3 simple steering rules with no game-theoretic design whatsoever, and asked, is there a hidden game lurking beneath the flocking? And using the sparse regression pipeline that we created, we discovered a latent utility structure that explained agent accelerations and turning very well. And when we simulated agents using this discovered utility function, genuine flocking emerged. So a game was actually there all along, and we just had to look for it. So what does this mean, and where do we actually go from here? Right? First, we see that emergent collective behavior encodes recoverable information about the rules that generated it. Second, that game-theoretic structure may be a universal feature of emergent systems, even in systems that were not actually designed that way. This opens a fundamentally new direction. Instead of handcrafting local rules and hoping for the right global behavior, we could actually one day specify the desired emergent outcome and infer the utility landscape that produces it. That is the pathway to designing collective intelligence and not just observing it. Thank you.